Okay, for this week's problems, I have some mixture of relatively straightforward and then some that are require a little bit more thinking and then perhaps some algorithms. So we're going to go through these one at a time and then let's see how to do them. So the first problem is the new alphabet. And basically what they do is they give you an input string. Okay, input string can be any characters in the ASCII range 32 to 126 as well as tab, number 9, but only characters A to Z and A, capital A or little a should be translated. Any non-alphabet characters to be printed and not modified. Inputs has at most 10,000 characters. And then output the input text with each letter, lowercase and uppercase translated into its new alphabet counterpart. And they give you how do you translate? A goes to the S, D goes to H, but then some of them, for example, D goes into 2 characters. So some of these could be replaced by multiple characters. What should we say? So there are many ways you can do this. I mean, you can just do an if statement or switch statement, I suppose. But the way that I would do this is the following. I would set up an array string, I don't know what you want to call it, translate, and up to 128. And this will be indexed by the ASCII value of the character. And then at the beginning, I would just say for int I equal to 0, I less than 128, I plus plus, trans I is equal to the string consisting of itself with one character. Okay, so this is maybe a little bit strange, but basically this just say that for by default everything translates itself. Why do I have to do this? Because this is string and not a character. So I have to convert this character into a string. Okay, so now what I would do is I would write trans, like this. And then I would basically do this multiple times. Okay. Or if you want, you could actually just have another table string. Um, uh, so that's one way. So that's method number 1. Method number 2, you could have translate, and then this time I would only have 26. Okay. And I would just put A, and then B is what? B is 8, and then brackets and this and that. So I basically just write bracket this way, and then this way, and so on. I just do the 26 things. And how would you use this table? If you're using the first one, then basically for every character that you read in, so you have some loop that's basically while C in dot get some character, then in the first case I'll just say C out trans CH, and that's it. In the second case, I need to be a bit more careful. I will have to do the while loop, while C in dot get CH, and then if is alpha CH, then I would do C out trans, and then I have to remember that I have to worry about upper and lowercase. I just converted all the lowercase minus the little a. That will give me 0 to 25, 5, and then otherwise the C out itself. Okay, so either way, something like that. But what I want to say is instead of using if then else or switch statement, the better way is to use some kind of a table. And that would make your code a little bit easier. Okay, so that's really all I want to say about this problem. Okay, so let's see. Next one that I wanted to talk about is the quick estimate. Okay, so you can read the problem, but basically they give you a number. Okay, they give you, so there's first in the line is number n, and then the next n line contains one estimate cost, which is the number between 0 and 1 and 10 to 100. So that means it's the number that can have up to 100 digits, actually 101 digits. For each estimate cost, I'll put a number of digits required to represent it. Okay, so you read the 5, and then here's 3 digits, 1 digit, and so on. The point is, do not ever read this as an integer because it's going to overflow. If you're in Python, I suppose you can do it, but really you don't need to, because all you're asking is how many digits you need. Well, you just read this as a string and just print out the length of the string. So it's I don't know if you call it trick question, but it's relatively simple. You just read a bunch of strings, and for each string, print out the length. That is all you have to do. All right. What's next? Let's look at Robotopia. All right. So basically, what I have is that they have 2 different types of robots. The first type of robots each robot has L1 legs and A1 arms. And then the second type of robots has L2 legs and A2 arms. And then, but you don't know how many of each type of robots there are. You just know the total number of legs and arms that you have counted. And then the question is, how many robots of type 1 and how many robots of type 2 do you have that will add up to the right number of legs and arms? And so the output for each test case output 2 positive integers denoting number of each of the 2 types of robots. Give first the count of the first type listed. If there are no solutions or multiple solutions, just put a question mark. So you have to worry about no or multiple solutions. And all numbers are between 1 and 10,000. All right, so in this case, we don't actually need any number theory, because what happened is you have type 1 robots. Let's call it the number of such robots is C1, and type 2 is C2. These are the numbers that you're looking for. And the number of legs and arms for these 2 types are L1, A1, L2, A2. And then total, you're supposed to have what do they call it? LT legs and AT arms. So the total number of legs, it's going to be C1 times L1, the number of first type of robot, times the number of legs in the first type, and then the second type like this. And similarly, the number of arms would satisfy this. And at this point, you will say, okay, well, of course, the other thing is C1 and C2 has to be greater than or equal to 0. You cannot have negative numbers. So you could try to solve these equations using some complicated math. But the important thing is that all of these numbers are between 1 and 10,000. So what does that mean? If you have at least 1 leg and up to 10,000 legs for type 1, and also the total number of legs, that means C1 and C2 has to be, of course, at least 0, but at most 10,000. In fact, it's not even 10,000. It's at most the number of total legs divided by the number of legs of type 1. Okay? For C1, I should say. It cannot be. And same thing for C2. But anyway, it doesn't actually matter. We'll just say that, we'll just not even be so clever. We'll just say it's up to 10,000. Okay, why? Because if there are only 10,001 possibilities, we just try them all. So for each C1, for 0, 1, 2, all the way up to 10,000 or whatever, if you want to go up to this round, it doesn't even matter. What you're going to do is you try and plug this in. So whatever you have, let's say you try C1 is 5, then, well, then you basically just write LT minus 5 times C1. And C2A2 is equal to AT minus 5 times C1. So let's say you're trying, sorry, not C1. This should be L1 and A1. Right? So let's say you're trying C1 being 5. Well, if this is possible, if this is the possible answer, what does that mean? That means this right-hand side, both of these right-hand sides, okay, have to be, of course, greater than or equal to 0. And it has to be divisible by L2, and the second right-hand side has to be divisible by A2. If they don't divide, then you know that this 5 is not a possibility. If they're negative, if any one of them is negative, you know it's not a possibility. So you do that. If it's divisible, then you can compute C2. And presumably, if you have the right C2, then both of these equations will give you the same C2. And if both of these equations give you the different C2, then again, that's impossible. So basically what you do is you try all the possible C1s, solve this equation for C2 if there's a unique solution, and that's one possible pair of C1 and C2 if you find it. Try all of the C1s from 0 to whatever, to 10,000, and either you find one solution, you don't find no solution, you find multiple solutions, and that's really all you have to do. So it's a little bit of arithmetic. You write a loop that loops to C1, and then you check a few things, check that the two right-hand sides are both positive, greater than or equal to 0. Check that the first one is divisible by L2, second one is divisible by A2, compute the quotient and make sure that the quotients are the same. Okay. Well, that's it. There are other things that you could do. You can try to be more clever in solving them enough. So this is kind of a system of 2 equations in 2 unknowns. Although you do have to worry about the fact that you only want integer solutions and you want non-negative solutions. So there are things that you can do, but it's just not worth doing all of this for a problem this small. Okay. Now, let's look at the more, maybe a little bit tougher problems. Which one? Inverse factorial generated quite a bit of discussions online. So, yeah, what's going on here? So you're given a factorial. You don't know which factorial it is. You just know that it's a factor of something. And you have to figure out what this something is. So that you're given n factorial, and you have to figure out what n is. And the number of digits in the factor is at most 10 to the 6. So 1,000,000 digits. And so, for example, if they give you this big number, you're supposed to say 21. And then maybe a bigger number, you're supposed to say 27. Okay. Now, one of the things that I guess I put on Discord, where is it? I gave a couple of hints that I don't know how much of a hint this is. I said the first thing is that the input is guaranteed to be a factorial. So they're not going to give you a number that's not a factorial. And then I show you, the people here, that these are the first 20 factorial. Why did I do this? The reason is that if you look at after the first field, so suppose you go out, let's look at forget about the first 6. If you just look at 7 and on, and then later on, and it doesn't matter if it's 21 factorial and so on, every single factorial will have a different length, because when you multiply by something that's bigger than 10, you will guarantee to be at least 1 digit more. They're never going to give you 40,032 and 1. So if you know that the input has 5 digits, you don't have to do anything else. You can just say 8 factorial. So the main question then is, can we figure out how many digits there are in n factorial. Because if you just compute n factorial, this is going to get really big. They tell you that it can be up to 1 million digits. Even if you have large integers, let's say in Python, computing n factorial the normal way will take way too long, even since computing one single factorial. So how are we going to get this? So really, the main thing is this is going back to this other problem, the quick estimate. The trick, if you can handle the first few cases, is to figure out how many digits n factorial has. Or in general, maybe how many digits does any number have? Right? I give you a number. How do you figure out the number of digits? So let's think about this. So if you have a certain number n, so forget about n factorial and so on. I'm just looking at a certain number and how many digits you have. Right? You start with 1. Of course, if you have 1, it's 1 digit. But it's not just 1. Any number from 1 to 9, you have 1 digit. Any number from 10 to 99, it's 2. 100 to 999 is 3. Okay, so I'm writing things that you're probably not very familiar with, and so on. Now the question then is, how, if you don't know what the number is, right, can you come up with a way to compute this from n to the number of digits without actually, I guess, counting, or convert it to a string and then print it out, because this has the number that we're looking at has many more digits than we can handle in a normal, even a 64 or even 128 bit. So what are we going to do? Okay. You notice that things happens when you get to a power of 10. It only happens when you get to a power of 10. So let's think about what kind of function can change from a power of 10. Well, log of base 10. Right? When you do log of base 10, things will change. So from 1, log of base 10 is 0. 9, log of base 10 is less than 1. So basically, I'll just write 0 to 1 like this. So it's a number, when you take log of base 10 of any number from 1 to 9, it's a number between 0 and 1, but not including 1. And similarly, so if you just take the log of the numbers and round it down, then you're almost at the number of digits, right? Of course, you're a little bit off. But if you just say log of base 10 of n, round it down, plus 1, this actually matches this exactly. Okay, so now what? If I get a number, right, I know how many digits. I know how many digits the number is by doing this. So if I have n factorial, how many digits are there in the n factorial? I don't know what n is, but whatever n is, it's log of base 10 n factorial rounded down plus 1. So whatever input I get, I'll get a certain number of digits, right? I'm going to compute this for n equals to 1, 2, 3, 4, and so on, until the number of digits match the length of the input. Again, I'm going to ignore the first 6 or 7 factorials, so you can just search for that. The small cases, it's easy. But assuming that you know it's not the first few cases, then what you do is you just try to compute this. And when you get the n that matches the number of digits in the input, then you're done. So why is this any easier than before, right? Because I still have to compute n factorial, which is not good. But the point is, why is it good? Because when you take log of a times b, you can actually replace it with log of a plus log of b. This is one of the laws of logarithm. And of course, n factorial is just 1 times 2 times 3 and so on. And you can replace it with log of 1 plus log of 2. And so what you do is you basically add, you start with log of 1, which is 0, but let's start with that. Round it down, plus 1. Is that the number of digits you have? No. Add log of 2. Round it down, plus 1. Is it the number of digits you have? No. Then add log of 3, then add log of 4, and so on. And then basically you get to the right answer. Okay. What else do I want to say? Now, you might say, well, I'm doing floating point numbers, and maybe this is not such a good idea. It's true that you have round-up errors and so on, but the good thing, I suppose, is that because every single thing after a certain point, every single in value would increase the number of digits by at least 1. So you're not usually adding things that are very small. So round-up errors could be not as important, but also we are adding things from smallest to largest, and that's usually a good idea when you add numbers, floating point numbers, to minimize round-up errors. Now there's another line of thoughts that some people have put out on the web, and they say, well, let's forget about doing things exactly. We'll pick some prime p that's large enough. So we'll just say large for now. And then we'll just compute n factorial mod p. Okay. And then we'll compute the input mod p. And if the two matches, then you probably have it. Now, if the n factorial that you're looking for might be, I don't know, 1,000, then you choose a prime that is less than 1,000, then for sure, both of these will be 0, because p will be one of the factors in here, and then you get nothing. Anything that's bigger than p factorial will be 0. So you need to get a p that is large enough, larger than the maximum n that you ever want to look at. So how do you know what is the maximum n that you ever want to look at? Well, it's basically this argument. You compute the number of digits of n factorial, and you realize basically how much for a million, you never need more than n being more than a million or something like that. Okay, it's actually much less, but that's good enough. So if you pick any prime that's bigger than a million, that's probably good enough. But that's a probabilistic argument, because just because two numbers are the same mod p doesn't mean that they're actually the same. It's likely, but it's not necessarily the same. So if you really want to be sure, you can pick multiple primes, or, I mean, the other thing to do, you can try to, compute the first 1 million n factorial mod p. That's relatively easy because you basically compute the loop, and for each n factorial you compute along the way, you can compute mod p. Throw it into a set, make sure that none of them collide. And if that's true, then you know that there's no possibility of error. And if that's not true, then you pick a different prime and hopefully you'll get something. Okay, or if you really want, you can have multiple primes and make sure that it passes multiple primes. Okay, so that's two different ways of doing it. But the main thing for me is to realize that you can't actually deal with n factorial the way it is given, it's hopeless. So you have to look for some other trick. All right, what else do I want to talk about? This. All right, so let's look at unusual starts. So you have a game of darts, 2x2 footboard. Alice throws 7 darts in a 2x2 square, and then Bob may or may not throw 3 darts. So the Alice 7 darts define a polygon by the order in which they are thrown, with the perimeter of the polygon connecting D1, dart 1 to 2 to 3 to all the way to 7 and back to 1. If the polygon so defined is not simple, meaning that it intersects itself, then Alice loses. If the polygon is simple, then Bob throws 3 darts. He's not a very good player, so although his darts always land on board, they land randomly. So if 3 of these darts land within the interior, Bob wins. Otherwise, Alice wins. So for this problem, you're given a location of Alice darts, which form a simple polygon, and the probability that Bob wins. Your job is to determine the order in which Alice threw her darts. Okay, so you're given the polygon, you don't know the order, and at most, well, there are exactly 7 of these darts that defines a polygon. And then you have to figure out an ordering of these darts that makes it possible for Bob to get the certain winning probability. Okay, so what is the so basically, if you can figure out the probabilities of Bob winning in a certain ordering, then what you do is you just try all ordering, because there are only 7 of them. 7 factorial is not much. So you try them all, and for each ordering, you determine the probability that Bob wins. And see if you get close to within 10 to the minus 5, and if so, you give the one that's lexicographically first. Does it say that there's always an ordering? Blah, blah, blah. I'll put the order in which the darts could have been thrown. Well, that's so far into several answers. It doesn't say what to do when there are no valid ordering, so I assume that there is a way. There's always a way. Okay, so this problem requires a bit of work, and certainly not for people that are starting out. So I'm not going to spell everything out. If you're going to look at this problem, you probably will know a few things already. So the first thing is you got to try all 7 factorial orders. And the way that you do it is in C++, use the next permutation function to loop through all 7 factorial, which is only, what, 840 or something like that. So 848. Then for each permutation, you can draw the polygon, right? So whatever polygon you have. And you can see if it intersects itself. How do you see if it intersects itself? Basically, for each line segment, you intersect it with all the other segments and see if it intersects at an endpoint or an interior point. And this can be done with the code library code. We have line intersection code in the code library. So for each line segment, intersect with all the other lines, right? And see if you intersect at any place other than the two endpoints. In fact, I guess you don't, for each line, you can intersect all the other lines except the 2 that you're connected to directly. Okay. If you intersect anywhere else, then you know that you're not simple. So the probability of winning for Bob is 1 because Alice loses right away. After that, suppose it's a simple polygon. Then you can compute the area of this polygon, whatever that area is. Okay. And then the total area is 4, 2 times 2, so it's 4. So what Bob has to win So Bob wins if he lands inside, okay? So the probability that Bob lands inside for each dart is basically A divided by 4, right? The total area of this polygon divided by 4. If this polygon is big, then it's higher probability. If it's low, then it's smaller probability. That's the probability that one dart land inside. He has to throw 3 darts independently. So you raise to the power 3. So what's going on? So once again, to recap, for each permutation, so you can use the next permutation function to step through them. Check if polygon is simple, right? So the line intersection Z. If not, probability of winning is 1 for Bob because L is lost. Otherwise, A is equals to the area of polygon, and then probability is A divided by 4 raised to the power 3. And then after you computed the probability either way, check if probability is close to input, whatever they tell you the winning probability is, and if so, you're done. Report the answer. So mostly this is an exercise in using the geometry library routine and figure out which one you need to use. All right. The last problem that I want to talk about is this big truck. So you're given a graph, okay, so you're given a graph and these edges have weight. You want to go from one place to another, 1 to 6, for example. And then in each location, there may be parcels that you packages that you can pick up. So the idea is that you want to go from 1 to 6, your start to destination using the shortest path. But at the same time, if there are multiple ways you can go from 1 to 6 with different shortest paths, you want to pick the one that allows you to pick up as many packages as possible. And picking up packages takes you no time. So the only cost is traveling in it. And what do they say? There are at most 100 of these locations. Each place has a certain number of things that you can pick up, 0 to 100. The edges from A to B. And I believe these roads are bi-directional. Yeah, all roads can be traversed in either direction. At most 1 road between any 2 locations, and no road starts and ends at the same location. And you want to go from location 1 to location N. If there's no way to do it, you say impossible. Otherwise, you find the shortest length of the shortest path followed by the maximum number of items you can pick up. All right, so if you don't have to worry about picking up the maximum number of items, and this is just the standard shortest path algorithm, because there are only 100 nodes, you can use pretty much anything. You can use Dijkstra, you can use Freud, any method will work. The problem is, of course, that you have this extra condition that you want to not only take the shortest path, you want to take the shortest path that allows you to pick up the most number of packages. And again, this is a problem where you have to be familiar with some shortest path algorithms. So I'm going to assume that you know Dijkstra. In Dijkstra, the standard algorithm is that at each location, you maintain the index of the location and then the distance that you have discovered so far. So what do I mean by that? You have discovered, so this is the start, and you've discovered using from the source to the shortest place, 3, 5 and 7, that this is now the source, of course, the source of distance 0, then this has distance 3 because this is the shortest one. And then you look and say, okay, this one has no 1 and so on. So this currently, the estimate, the distance so far estimate is 5, 7, 4, and what number did I put it? So estimate 5. But then there might be another edge that goes like this to 2. And when I incorporate this vertex here, I would update this 7 to be a 5, because now that's better. And basically at every time, so put all of these things into a priority queue. And the next one to be incorporated as known is the one that has the smallest distance so far. So in this case, I would incorporate this 4 into the known side, which has now become, oops, why is it so thick? Becomes 3. And then see what other edges come out of this and update distances and so on. I always pick the one that is smallest distance so far. So that's the Dijkstra's algorithm in a very quick glance. And for this problem, basically, we're going to do something similar, except that we're going to add an extra that says the packages that you picked up so far. So not only are you going to keep track of distances, you're also going to keep track of how many packages you have picked up. So for example, if I'm updating, if I'm here, right, and I'm here, and I picked up a certain number of packages, then I can update how many packages, not only distance I go by following these edges, but also the packages that I update so far. And the only trick is when I update a number, instead of just saying, let's update this number, if we place it a bit smaller, I would replace both of these numbers if this distance is smaller, of course, because this is my first tiebreaker. But if it's the same, then I want to replace it if this number is bigger. So in other words, I'm basically looking at this as a tuple, and I'm going to first minimize this one. And if there's a tie, I want to maximize this one. And one way that you can do this, I guess, is to negate. You want to negate this packages, make it negative so that you're just taking the minimum of a tuple. If you do that, then basically all you do is you run Dijkstra's algorithm with priority queue picking the smallest distance possible, and if there's a tie, pick the biggest packages so far, and then expand. And if you run Dijkstra's algorithm, that's all you have to do. There's another way of doing this, and another way of doing this is to use Floyd's algorithm. So Floyd's algorithm allows you to compute all pair shortest path, which is very easy. It's basically three triply nested loop. And now you know the distance between any starting point to any ending point. Okay, so now what? How do you know if you can go? So let's say this is my start, this is my end, source and destination. How do I know that there might be multiple paths? Well, let's say the beginning, I have a bunch of different nodes. Which way can I go and still have shortest path? Well, if I know the distance between source and destination, and this is a node, whatever this node is, then this T is part of a shortest path if this is true. Okay, by going to T, there's a way I can continue so that the distance is not any worse. And I can kind of look at, basically I can eliminate all the T that doesn't work, right? So there might be some nodes that is not part of a shortest path. In those cases, you can get rid of it. You can pretend that they don't exist. Also, the other thing to notice is that if there's a T that goes this way, then there'll be another set of nodes that can merge. There could be multiple ones that merge together. But these edges will never, ever go backwards. Why? Because if you go backwards, the distance will be bigger, and it's no longer part of the shortest path. There can never be a cycle in this graph. So what you end up with is a directed acyclic graph where you start from the source, then you go to different distances, and so on. That could be merging, and so on. And then you go to destination. And whenever you have a directed acyclic graph, you can actually do, now that you know that by following any of these edges, you will follow a shortest path. From source to destination, it's always the shortest path, because we get rid of all the nodes and edges that don't allow me to do this, that don't satisfy this equation. And then basically what I do is I just run it for dynamic programming. What is the maximum for each point? What is the maximum number of things I can pick up starting from this point? And basically it will be the number of things I can pick up here plus the recursively all the maximum number of things I can pick up by starting at each of my children. And then basically you just start the dynamic programming from the top, from your beginning, and then as long as you do dynamic programming properly, it will give you the right answer also. So there are two ways you can do this. Normally, all pair shortest path is a bit of an overkill for this problem also, but because n is small, n-cubed algorithm is fine, and it is way faster to write this. Right, it's just 3 loops. Okay, anyway, I think that's it. That's all the problems that I have to talk about today. And I guess next week I'm not going to post any new problem set because NAQ it's this Saturday, and then I guess next week I'll talk about NAQ.